it does a barrier. Okay, then let's start with 23. Let's make it bigger, maybe, for you to be easier to identify them.
How can I access that color tab?
Yeah, you double click and you go to colors.
Yeah.
Okay, let me take out this.
Yes. Yeah.
I can make this window bigger. Sorry. What is doing? Okay. I think this is a problem with Zoom because typically it's not so slow. Okay. So we have read process 23. It does receive, vsend, barrier. And this is the same from process 2 to 23. The first process does not do the receive, it does the vsend and a barrier. Okay, so reading the sequence, I can see basically except the boundaries, all of them has the same pattern. They first receive, then they do a send, and then they do the barrier. So this image tell us, this pattern of communications, this connectivity pattern tell us to whom I am talking, okay? So if I am process 1, I'm talking to process 2, okay? If I am process 2, I'm talking to process 3. I can do the same thing here if I do view communication lines, okay? So basically what we have here is a pattern where each process is talking to the next one, okay? And what's the problem? Basically, if you see this process, basically this process has to wait until all the previous ones have made the communications in order to do the reception, okay? Because basically the round number, the second process receives from the first one, while the third one is already waiting. Once this communication takes place, then you start the other, okay? So you see the change of the communications, yeah? Then my question, and I will give you 2 minutes because we are a little bit short of time, is what is this code doing and how you will improve it? Just think a little bit about it. If you want to share some feedback, please talk, that will be great. If not, at least think about it. But basically, what is this code doing and how you can guess what is the source code? Apart from what I have been telling you, what is the semantics of this communication pattern? And I already can give you a hint. There are 2 options. Okay? The same pattern can be expressed in 2 options. So if you find one, try to find another one. Okay? And I give you 1 minute and a half. So anyone has any insight on what that is doing? Okay, let me explain you the options, okay? And then if you have any question, just let me know, okay? First option, and basically the options depends on the data, okay? First option is the first guy has a data that sends to the second one. When the second one receives that data, it sends to the third one, and so on. So the same data is sent to all the processes. And it's done one by one because until I have that data, I cannot send to the next one, okay? If this is the case, the solution is simple. I can change that by a collective, a broadcast that will automatically do that on a better performance way than my code, okay? Does it make sense? I hope you are alive and I am connected.
Yes.
Okay.
I thought that these processes were interchanging boundary regions, maybe. But probably, yeah. But if they, I don't know, if they are moving things around, then probably broadcast will
Yeah,
be.
one option is if they are moving things around, you cannot use a broadcast. Okay, and let's say the problem is that the programmer didn't know about the broadcast or was confused, and it generates this delay. And as you know, if we are 24, that's a problem. But if we are 100, that's a huger problem, because this scaling problem will be worse and worse when we add more processes. But what happens if it's not the same data? It may happen that the data is different. And then the reason is that basically the programmer didn't take into account also this issue, okay? And it makes a receive that is blocking before doing the send of the data. But in fact, the send can be done before. And then if I do, for instance, and I receive and then I do a send, that will be a way to block that part, okay?
So the key thing here is, because there is no computation in the middle, we should be able to parallelize the moving of data.
Yeah, basically we have to know. We have to, let's say, what the trace file is not able to tell me is about the data. It's not able to tell me if they have the same data or not. And in that sense, I can only make hypotheses that I can verify with the source code. But basically, the analysis of the trace file already tell me there is a efficiency problem, okay? Because this is telling me this is 60% of the time inside MPI, this region. And it's 60% because I have these two regions here. If I make it on this pattern closer, then it goes down to 7% of the time computing. So it means 92% of the time is doing MPI, because it's basically zooming on the MPI phase, okay? And then you make the guess on the data to decide how to improve the code. So basically, in the performance analysis, I detect this is a pattern that is causing me scaling issues and that is causing me a waiting time that is not needed, okay? And then the solution will depend on the data. And I only have one of them implemented. I can go back to the feed time scale that may be faster, okay? Because I just have 1 more minute. But if I zoom here, okay, I have here the pattern where I do an ISEND and then I do a receive. And then all of them take place in parallel, okay? So let me clone that window, okay? Let me take out that from the synchronization. Then me go back to the full scale. I'm just going to look for the one I have seen before, okay? I can just go here and then copy, and I go close here, and I do paste the duration. Okay, and now I can compare. This is, if I do this sequence of receive, descend, and barrier, or I do, well, here I don't have the barrier, but basically the barrier is absorbing the imbalance. If I do the ISEND and the receive, okay, you can hear a feeling of the difference of the duration, okay? So in this range of 24 processes is around 10 times faster, okay? And the only thing is to change the primitive of MPI. So this is just one example, okay? It's just to give it a flavor of identifying with the trace file, reading the trace file, identifying patterns that has problems of efficiency, and depending of the pattern, you have an MPI solution, okay? This is a very simple case. There are cases much more complex, but what you, let's say the main message here is, if you see something that is kind of a triangle, be scared and worry about it. You need to fix that, because if you increase the number of processes, you will be die, okay? And I think we should stop this hands-on now, so we have time to get the trees and have a look before the break for lunch from 1 to 2, okay? Later we can decide if this afternoon we want to have a better analysis of this execution. Just as a reference, let me, in case we don't have a look and you want to have a look on your own, okay? If I go to, sorry, I don't want to do that, synchronize. If I look to one of the iterations, okay, you have in this first part, you have 3 patterns. We have been looking at the first one, okay? And you have 2 others that you can also try to understand. They are a little bit more complex, but in fact, they have the same behavior. If I do I don't look at the communications, okay? I see triangles, different shapes of triangles, but all of them have. So all of them suffer for something similar, and you can dig down what is the case, okay? And then in the other part of the communications, you basically have 2 different options to see. I have a perturbation here. Let me copy and paste the default. I have a small perturbation in one process, and as we have seen in the slide, how this is propagated to the communications through the communication pattern. And see, for instance, the difference depending on the primitives you use. Here, all of them pay at the same iteration. Here, on each of the iterations, one pay for it, okay? And then the barrier absorbs for the ones that have not paid, okay? So in case we do not go back to this example, you can have a look if you want, okay? So I stop talking and sharing, and then David will help you to get your first trace file and have a look. Well, if there is any question, I can answer quickly. Okay, I think, David, you can start.
Let's move on then to obtaining traces then. No, let me just show the entire screen and then I will share desktop 1. This is it. All right. Okay, in this section, we're going to try to generate these traces for ourselves. Okay, but before getting into it, I'm going to make a brief summary of what the main features of Xtri are. Okay. So the first thing is that Xtri is a library that works in any kind of architecture. Here I have a list of the most common seen ones. The second important point of Xtri is that it works with the following parallel programming models. Okay, this means that it can obtain the information about the behavior of these programs in the application, and to do so, it interposes or intercepts the activity of the runtime of the given parallel programming model, and reports what it's doing in that instant. At the same time, it is able to obtain counters about the performance. We do so by using the PAPI interface. So up to this point, what we have at a given moment is the information about what is a parallel runtime doing, like MPI, as we have seen the activity, could it be an MPI send or a collective call? And with that, and at that same time, we will also have the counters of the performance of our machine. Okay. Another key of this tool is that we're able to link this information regarding the runtime activity to our source code. And we have several ways to do so. For MPI, we can obtain the call stack, which is the routines that has called the MPI directive, okay? For OpenMP, we get the name of the routines that are encapsulated by the Pragma parallels. And we can also provide a list of user functions. So we get data at those points when they get executed, okay? And Xtri also provides the possibility to use periodic sampling in case we want to obtain information in those areas where we don't have runtime activity. We could configure with a small enough value to get counters at those given points. And finally, if we need even more detail about this, we could introduce Xtri events at any point in our program by using the Xtri API. For all these features, except the last one, there is no need to recompile or to compile it in Xtri against your application, or your application against Xtri rather. But when you want to use the Extrai API, you will have to compile it against Extrai. Okay. Now, as I was telling before, these events that have the information about the MPI activity or the runtime activity, they can also have the information about the counters that are happening at the same time. Okay, and so we have the different time that it costs to generate these events. Okay, if we only want information about the runtime activity, a single event takes this amount of time. If on top of that we want the information about the counters, like the number of cycles that it has in that point, and or the instructions, or misses in the catch, okay, this goes up to 70 or 751 nanoseconds. And if on top of that we want the information about where is it coming from, this keeps rising. Okay, the more levels we add to the call stack, the more time it gets, it consumes. Okay, so this is important to consider when you are working with a short application or a small application. Okay. And now briefly, let me tell you how Extrai manages to get this information. Okay, the most common way and the main way that we're going to use, and the way that we're going to use in this training, okay, is by using the LD preload. And by defining this variable here, we can interpose, or we can guarantee that our Extrai library will be interposed before the application that we're trying to trace. Okay, in this way, any symbols that our application calls from the runtime, for a particular runtime, let's say MPI, will be solved through our library first, and then we will call to the runtime library. And that's the point where we use to introduce the information about what is happening and the performance counters. Okay. Another way to do this is by using another way Extrai does this is by using the Dynins library, which allows us to interpose to any kind of routine, not only runtimes. Okay, but since the recent update in their version, we have lost partial support of this feature. Okay, and the last way to interpose or Extrai mechanism, or what the Extrai mechanism is to interposing the runtime, when we do it statically, we use the profiling APIs that the runtimes provide. In the case of MPI, we have the PMPI, and so that is given by the MPI library precisely to intercept and instrument their calls. And now let's move on to how we're going to generate these traces. Okay, there are just a couple of important steps here. The first thing will be to adapt our job script, which we use to launch and request resources in the Mare Nostrum machine. Okay, and the second important thing is that we have to provide a configuration file to indicate or configure what information we want to obtain in the execution. Okay. If you want to know more information about how we should configure different information for execution, or if you want to know what kind of information can be obtained for an execution, please refer to this web over here, which is the manual or the user guide for Extrai, okay, which is also distributed as a document with the installation. Now let's move on to Mare Nostrum. Okay, so the first thing I want you guys to do is to connect to Mare Nostrum by using your user as shown here. And when you are done with this, please report it with a reaction. And there you can find the list of these, well, you already seen this, the different different folders that we have for this training. What we're going to use now is the extract folder to obtain the traces. So there's for people that have this already done. If at some point you get lost, or do you want me to go back and forth on these slides, just say so, and I will go there. You also have these slides under the name of Extrai and Paraver hands-on in the slides folder. I mean, could I? What I'm gonna do is I'm gonna leave this command in the chat and move to the next slide so we can go a bit faster. Where is the chat here? Okay. So this is H, Y, your user, at, well, the login machine you want, esc.s. Now, let's take a look at the JavaScript file that you have in the directory of Extrai. Okay. The one that you have there already has the modifications needed to launch your application with Extrai. Okay. Here I'm showing you only how we would launch an application to see how it changes when we want to adapt it to use Extrai. So two important things about the request of resources. The first thing is that we have to select the amount of 27 tasks to use, because this application works with a cubic number of tasks. And the second important thing is that, well, it's not as important, but to use the reservation keyword that they gave us, so we can have preferences in the execution on the machine for the day. Okay. Now this would be the launch of the application itself. We have the MPI run call, followed by a flag that what it does is to make sure that the task is assigned to a core. Each task is assigned to a core, and it does not migrate if the operating system wants to, you know. This is the application that we're going to use now. I'm not going to enter into details of what this application is or what it does, just to show you that we can work without knowing the application itself. Okay, and these are the parameters for the application. Now, the first thing that we have to add to make use of Extrai, at least in Mare Nostrum, is this constraint over here for the Slurm manager. Okay, it is required for security reasons since 2022, I think, in all the BSC machines. This allows us to access the performance counters to get the readings there. Okay. Now, in the same way, this is a thing from our BSC machines. We load the Extrai module, so it sets us, it setups to us the different paths that we will use in the trace script. Okay. This is the optional name that we can give to the output trace. Okay. And you will see that we have added here, right before executing our application, this trace file script. Okay, let's see the content of this file. So here we're indicating two main things, which are the ones that require Extrai. The first thing is, where is the configuration file? And you have seen that I have not only given you the JavaScript for this example, but also the configuration file. It's at the same root, or at the same folder, I mean. And on the other hand, we also have to configure the LD preload, as I've showed you earlier. We could I mean, we could set here the absolute path to where this library is, but this variable would work because we did the modular load before, okay? The important thing about this, about selecting the library that we're gonna use to intercept the information, is that we provide different libraries for different runtimes, and I'm gonna show you in the following table. So, as I said, Extract, what it does is to implement the symbols of a given library. So for that we provide different libraries that have the different symbols that these different runtimes use. Okay, if we're working with MPI, we only have to use the libMPI trace, which will implement the symbols of MPI. If we're working with OpenMP, the library is called OMP trace. Okay. If you want to work with a combination of both, we have this one over here that has both of those symbols. Now, the next thing is, if the application is in Fortran, the name of the library ends up with an F, okay? In this case, this application is, I think it's implemented in C++, or it could be in C. So we're gonna use only the name of the libMPI trace without ending in F, okay? Once selected the library, you just have to point to where it is, okay, with the LD preload, and then we move on to see what the configuration file contains, okay, and what are the main features in here. So the first section allows us to select and enable and disable the different runtimes. Okay, for this application, this only works with this only has MPI, so we only need MPI enabled. Okay, and the next section configures if we want to obtain the color stack for MPI. Okay, or, well, not only MPI, but we'll also work with sampling. With the color stack, okay, and how many levels of this stack we want. Now, if you go a little bit down, you will see that there is a section that this section is important. Is the one that configures the counters that we're gonna read. And here we use the labels that are provided from PAPI. Okay, these are not our keywords, but rather from PAPI. And we can define a set or different sets of counters in order to read all of the counters that are in a given set all together. Okay. In our example, we have this defined, and thus when we find an MPI directive, all these counters will be read at that point. We could define several sets with different counters or the same counters just to read a different group of counters all together, and play with the configuration of time to change from one to the other. And for our example, we only will work with one set, and in particular, the most important counters are the instructions and cycles to analyze or at least to make the first analysis of the performance of the application. Okay. Now moving lower, we have the buffer, which allows us to configure how many events we will hold in this buffer. Now, mind you, this buffer is stored in memory. So here you can play, there's a trade-off between how much memory I'm consuming and how much time I am losing whenever we have to flash, because when we fill this buffer has to go to a temporal file, and that is costly, okay? And here we can see also the possibility to configure a sampling. This sampling could work, this sampling allows us to configure, allows us to rather gather performance counters every so often, as configured by here. Okay. We will not be using this in our training for today. Okay. And finally, we have the merging process, which what it does is to combine all the temporal files that have created that Extrai have created with all the events occurring along the execution and generating the Paraver trace file, which is composed by the PRV file, PSC file, and row. Now, please move on to the Extrai folder and submit your job by using this command. I wish I could have the chat here to see if someone is asking anything.
David,
Yes.
would it be that the job script is named job Intel instead of job Lulesh?
Oh, maybe yes.
Okay.
But let me
Okay,
just
there's
I
a
could
question.
connect and check.
Yeah, job Intel 27p. Yeah.
It is
The
okay.
system is also Job Intel. Yeah.
But
So,
the content
oh.
should be the same, right?
Yes, it is the same.
Okay.
Let me how could I fix this? Can we could you tell me if it's separated by a dash or a dot? Or is this just job Intel?
No, it's a dash.
It's a dash. Okay.
Yeah, it's the same thing, but instead of Lulesh, Intel.
Like this? Sure, I
You
check
have to
it.
remove Lulesh.
No,
not
without
Intel.
Lulesh.
Without Lulesh. Okay.
Mhm.
Now, if you well, once again, I'm gonna copy this command in the chat and move to the next slide. Okay. Job Intel, Okay, this is a batch. (27p.xh). There we go. And now you can check how your execution is going with the command with the SQ command to see if it has already been executed or not. If it has been executed correctly, you will have these three files in your folder where you call this command from. If you have these files, please let me know with a reaction in the chat. And I move on to the next section. We are at 25. Fantastic. And I move on to the next section, which will be looking into these traces and opening them with Paraver and analyzing them a little bit. The reactions are seen here, right? Okay. 6, fantastic. I will also use this time to tell you that for this following section, I will be doing it live and not using these slides, but you have these slides to follow along if you get lost at some point. Okay. It will lay out the same steps that I'm gonna use in the following section. Or even if it's needed, just ask and I will review any operation and re-explain anything that has been said. Let's see how we're going. This 11. Okay, and how many are we? 39. With okay. Well, I assume that the ones that are not showing that they are completed, it's because they are in queue, the job. So I'm gonna wait a couple of minutes because maybe there is some issue.
Can we check the queue? Is someone connected to Mare Nostrum to check the queue?
I don't have the account or the password for the. Could some of you do it? But I mean, it shouldn't take more than, let's say, 3 minutes. I think we are right on time. So
We have 8 nodes allocated to us. If there are 35 persons submitting jobs, they will enter by teams of 8. The run is very fast, but some of them may need to wait a little bit.
I'm trying just
And-
now,
and as-
and it ran in 10 seconds. So.
Oh, well, then everyone should have the traces. And if someone could not obtain the trace, I have already provided you I have already provided you one. That's the one I'm going to use for the following section in the folder traces, which has this name. Okay, so let's move on there. I will leave this as a background, or even just remove it. So, well, maybe I could use the first steps so we can, yes. So now that we have the traces, or even if you don't, you can find them in the traces folder instead of extract, but it would be great if you use your own traces that you have obtained. You can copy the same one you did earlier to your laptop, okay? Using the SCP and your user, copy the traces, all the 3 files by using this asterisk over here and to your current directory. Once you have copied these files and you have them in local, okay, go to Parabér and load the trace as you did with the example which you did. Let me do this. Let me do this as well. This is gonna be the bind. This. Oh, I already have one. Well, and you'll see that for this section, what we're gonna do is to follow the tutorials that you have downloaded earlier for Parabér. Does someone has any question? I can barely hear someone.
Yeah, it's my background noise. Sorry.
Oh,
I
okay,
have-
okay.
Sorry.
It's fine.
You in the previous slide, I think you had PWD. What does that stand for? I mean, I know what's present directory.
Oh, it's
working directory.
it substitutes your current directory. You could also use a dot here just to.
No, I know. I'm not asking for an explanation on the script on the instruction. What directory should that be?
Oh, it's whatever you want to use to
Okay.
do these trainings. It doesn't.
All right.
There is no importance there. Cool. Okay. Well, once you have these traces in local, let's move on to open them in Parabér and let's try to analyze them. How would we approach this first analysis? Okay. What we're gonna do is to follow these tutorials that you have downloaded earlier. In particular, the third one, well, if you have not downloaded all of them, the one that is called Introduction to Parabér and DMMAS Methodology. Okay. Now let me just put this aside and do it. In fact, I'm gonna just minimize this so it doesn't bother the wideness of the screen. So the first thing, on where should we start when we are trying to analyze an application, is to ask the question of how efficient is this application running, okay? And to do so, the tutorial recommends us, let me just use the tutorial as well. The tutorial recommends us the following configuration file, which is the MPI stats. And here, let me explain you briefly what this window contains, okay? We have, or we can see here, that number of tasks and in every column, and the different MPI routines in every row, and the different MPI routines in every column, okay? And an extra column on the left that is showing us when we are not in an MPI routine. And as you did show earlier, the efficiency model here, or that we use, we obtain the parallel efficiency using this time, the time when we are not in a runtime, in a parallel runtime, okay? And in particular, the parallel efficiency corresponds to the value of the average time spent not doing MPI. Okay, so the parallel efficiency for this application is 90%. Okay, then we also have the two components of the parallel efficiency: the communication efficiency, which is the maximum value of this of the time spent not doing MPI by a single rank or by one of the ranks, which in this case corresponds to 99.5. Okay, and the load balance, which in here is derived by the division of these two. Okay, because
Sorry-
as you did
sorry,
show
David.
earlier, yes.
One question. How did you open these extra statistics?
Oh, first I've went to the tutorials.
Yes. I
And-
mean the average and the statistics below the table, the main table.
Oh, I see.
You have to scroll.
So yes, the table previously is
okay.
shown like this, and
Yeah.
you can either scroll to the bottom or just as I did, I made the screen bigger.
Yeah. Sorry.
Sorry, I should have said this. Yes, at the
No,
bottom
sorry.
of every table we have the summary of per column.
Yeah,
Okay,
yeah,
and in
thank you.
particular sorry.
Can you repeat which part of the tutorial is that? Which number?
This is the Paraver and DMMAS. Let me see if I can find. No, it cannot. Let's see. How about this? No, it opened again. Maybe Introduction to Paraver and DMMAS methodology.
Okay, thank you.
Okay.
Yeah, stats. Okay.
You can
that's-
also reach this. Well, never mind. Let's continue from here. And yes, then we have a parallel efficiency of a 90%, a communication efficiency of 99%, and a load balance of 91%. Okay. Now, before continuing with this analysis, I want you to explain or introduce you to the concept of a focus of analysis region. I think you did show this earlier as well. And if we go back to the timeline that where all this data is coming from, by clicking here in the top left corner, you'll see that this selected window has changed to the one on the top. We see all the all the MPI activity during the execution. Okay, and the point I want to bring here is that we can omit the initialization and finalization of this execution, because we can assume that the bulk of the program, the core of the execution, is gonna be in the iterative part. So what we have to do here is to try to identify where these iterations or where this iterative part is, and try to focus our analysis just in that region. Okay. So if I hover over these values, I can see the different MPI calls. If you see in the label at the bottom here, and we here find the MPI init, for example, and this one that is very noticeable is a collective MPI all reduce. So one can argue that these collectives could either be, well, in this case it's an all reduce, so it's a little bit easier to distinct, okay? But these collectives can either be spreading. I'm not sure if this is the right word, but spreading the information. I mean, spreading or sharing the information for starting the computations, or rather accumulating the results from each iteration. Okay, in this case, this is an all reduce, and it tends to be at the end of the computation. So what I'm going to use is to select the information that goes right after an all reduce. This collective here has been completed up to the end of the last one. Okay. And now we will focus for the rest of this training, we will focus this section of analysis, we will focus all our calculations in this region over here. Okay. Now, what we want to do is to recalculate these efficiencies, but for our new region defined. Okay. So to do so, we right-click on the timeline window and copy its properties, and then we move to the table, right click on any point of the table and paste the time of that we have copied. And you'll see that this will recalculate or will do the or calculate efficiencies only for this region. They have slightly changed. Now here we are not taking into account the initialization and finalization of the application. Okay.
Isn't
But-
that synchronizing the windows?
Yeah, let me see. I'm not sure if I can. Yes, you could synchronize the windows, yes, between this and this one as well. This could be an option. What was I saying? Yes, the parallel efficiency, right? Now, from the two components of the parallel efficiency, we see that the communication is way higher than the load balance, and therefore we now have a new question, and is what is happening with the load balance? Why is it so low? And can we identify where? Okay. So to keep analyzing this application and trying to figure out what is happening to the load balance, what we have to see now is the distribution of the duration of the computations, okay, of this application. To do this, you will see that in the tutorial there is a I could open this. There is a suggestion to go to the useful duration CFG, okay, and we will do so. Is it the useful duration? To the useful duration? Oh, it's not exactly the same name, but this is the same window, okay. And now let's take a moment to understand what we are seeing here, okay. Let's remove all of this just to get a clear vision of what we're seeing here. Now in this in this table, what we're seeing here is the same in the previous one, ranks in the different rows, okay? If you see the label is at the bottom of the screen right here, okay? We see that in this case, this is the rank 27, okay? And over here, up here, we have the first rank. Now in the columns, what we have here is duration of time computing. So we have smaller durations on the left and larger durations or longer durations on the right, okay? You can see here, and this value is represented between these parentheses at the bottom, okay? So this corresponds to durations around 3 milliseconds. No, is it 3 milliseconds? Yeah, it could be 3 milliseconds. 3 nanos, micros, millis, yes, 3 milliseconds. Whereas here we have a 171 milliseconds. Okay, now it's important to notice that this is not a timestamp. We are not moving along the execution of our application. We have all the information from all the execution in this window. What we have here from left to right is durations. Okay, now let me explain what the contents of each cell is. Now that we know what every row and every column is, the content of every cell is the accumulated time that a particular task spends executing durations of this of where they fall. Let me show you better with these two over here. See, this one in the this one here in the right side corresponds to a duration to 176 milliseconds. Okay, 176 milliseconds. And you can see at the right side of the equal sign, we have the exact same value, 176 milliseconds. This is because there is only one duration of this longitude for this task, okay? Whereas this cell over here holds the values that last 171 milliseconds, okay? Which is less than 176. But the accumulated time that this task spends doing these types of durations is more than a second, as you can see in the right side of the equal sign. Now, this value as well determines which color the cell will have. If the values are low, the color assigned is a light green, and it gets darker the more time it spends doing that kind of duration, okay? Now, now that we know what this window presents, let's do again the same thing that we did for the previous table. We don't want the information of all the application, but rather only the part that for the one that for our iterative part. Since we already have copied the properties of the window, we can go here and paste the time, or as I think Miguel said earlier, or was it Daniel? I'm not sure now. We could also synchronize this with one. Okay, let me just use the paste the time, and you see that some of the values have been removed here because they corresponded to the initialization and finalization of the application. Okay. Now, how can we interpret this? Now, how can we take something from this view over here? Now, ideally, what we would want to see here in the durations of the different tasks is that they all share, or they all do the same amount of time of computation. Okay. What we would want to see here are vertical lines like these ones over here. But the thing is that these regions over here are fairly small, so they are not as important as this one over here, which is fairly straight, okay? And therefore, that's why we have such a high load balance, because 90% it's not bad at all, but we have to pinpoint where this 9% or 10% is coming from, okay? And that is this region over here, that we can see that this is not a vertical line, but rather some tasks, like the first task here, is taking a lot of time doing these computations, whereas this task over here is taking way less time doing these other computations. Okay. Now, the next thing that we have to ask ourselves is, well, why? Well, then why is this duration so different for these different tasks? And right away, the main thing that comes to our mind is that the work has not been well distributed. Okay, that could be it. So now we move on to checking the performance counters that we have gathered. In particular, we're going to see the instructions, which corresponds to the amount of work itself, right? So we go to the PAPI counters. I think this is suggested as well in tutorials in the following link, okay? And from the PAPI counters, we select the useful instructions. Now let me make this smaller and try to fit this to the side to see them both at the same time. And there we have it. Okay. Now, once again, we have to select only the region for our focus of analysis. Okay, by pasting the time or synchronizing to the window, to the first window. And I will see that not much has changed, but we can see here now the different patterns that the instructions are having. Okay, we can clearly see here that this region over here, all these tasks are executing this amount of instruction, the similar amount of instructions. And we could say that they clearly correspond to this other vertical line here. So this amount of instructions, same amount of instructions, are taking the same amount of time. A bit longer, but the same amount of time. The same we can say for these other vertical lines here, that they correspond to these durations over here. And finally, we can see that the same pattern that we see in the duration, we see in the instructions, okay? And we see that, as I said earlier, now what the contents of each cell is instructions, okay? So this task over here is executing more instructions than this task over here. And fair enough, it's taking more time to do so than this task over here. So there you have it. We have seen the correlation and where this imbalance, the duration of this imbalance on balance of duration comes from by checking the useful instructions. Now, the next thing from here is to try to find them. Where do they fall during the execution? Okay. To open where the window where this data is coming from, we have previously used this button over here. But for this part, we're going to use this lens that filters this view, this source timeline, to only the region that we want. So if we press the lens over here and select the region, you'll see that it will open the timeline with the useful instructions in it, but only showing us this region that is problematic. Well, you can see that it also has taken into account this one that is in the middle here. But okay. Now, what we want is not to use the colors from present in the timeline, but rather to recalculate the colors here with only the values that are present here to distinguish them better, okay? Because all this seems like the same color. And to do so, as the same way Judith did earlier, we go to the fit semantic scale and fit both. And now you see that this coloring that represents instructions are well correlated with the durations of the phases where they are. Okay, these ones that are taking more time executing are using more instructions, and these ones that are taking less time executing are doing less instructions. Okay, and this is what creates imbalance. Doing more and less work at the same time is what is creating this imbalance here. Now, finally, just to end this analysis, we want to see, or we want to find where in the source code this is happening, okay? To do so, we're just gonna center in one of these iterations, like so. And we have two ways to find where this is happening. The first way is by loading the call stack reference color function, which will tell us what's the name of the function that has called these MPIs that are falling here in this gap between the running section or region. And we copy the properties of this window and paste them here. Well, let's paste all just so it gets the same size. And now we can see that on the right side, what we find here is let me see if I can show well, kind of. Okay. On the right side, what we have here is this function. So this computation is encapsulated by these two these two routines, okay? On the right side, there is this function, and on the left side, if we zoom in, we can see that is this bluish, what is called this color? Aquamarine or something like this. It's this routine over here. But we can even go further by looking at where is the line that has made this MPI call. And in the same section as call stack reference, we go to the profile color line. Here we have all the lines of our application that has been traced. Okay. In this table, we want to see the same. We want to see the timeline where this comes from to see them draw alongside the execution. And again, we just copy and paste the properties from one window to another. And here you can see now that at the right side, this is happening at this file, lurich.cc, at line 186. And on the left side, well, let's see if I can show it. This routine over here, well, this may be a routine later on defined, okay? It's coming out from lulesh-com, okay, from the line 1824. And that would be it. This ends our analysis. Now, a couple of things. What if we want to save all this? Well, not the steps, but rather the final result of our analysis. I could go to right-click on this window over here and save this as a configuration. Let's give it a name, instruction and balance. And now we can load the configuration whenever we want by going to, I don't even know where I saved it, but we can load it later on, okay? And
David, you have it
Yes.
in load previous.
I see as well. Yes, that as well. True. You could also use the previous configurations because you just saved it. Okay. And this is it. This would conclude this part of the presentation.
You can also show them how to save the session so they save the full windows if they want to continue after lunch or they want to share with someone
Yes,
else.
sure. That's quite useful, actually. Yes, you're right. Definitely right. So you could also save these windows from another way that is shown in the slides. Okay, you could save these configurations from here and select all the windows that you want, or you could also just save the entire session right away by pressing save session and giving it a name. And then when you launch Paraver, you can just load the session and it will load all the windows at the place where you left them and all the informations at the way that you have calculated them earlier. Okay.
Yeah, and even if you have multiple traces, it will load all the traces, each one with their own views. Yeah, let's say you will recover everything you have saved before stopping Paraver.
Yes, that is right. So yes. Yes, let me go back to the slides then and see if I'm missing anything else at the end. We have correlated this. We have saved this, the configuration. All right, and now I want you guys to generate the trace, modify the job script to generate a trace without the flag that binds the tasks to the course, and try to see how the things have changed. You will use this trace as well later on with some of Judith's examples. And that would be it. If you have any trouble generating this trace or any questions about this section, please feel free to ask. We will be here for 5 minutes. At 1 o'clock, we will have a break for a meal, and we will see you back at 2 o'clock. Is it right, Judith?
Yeah, 2 p.m.
Okay.
So the idea is when we go back in 2 p.m., ideally you should have already this new trace file. Okay, it will be not the first thing we will use, but it will be nice if you already have it. Okay, so you now know how to process that. So basically, you submit the JavaScript, you get the trace file, you can either compress or not, and you bring it back to your computer. Okay.
Let me see if I can find the questions in the chat. Let's see. Check with the SKU. No, nothing here. Fine. And I'm move on.
Yeah, for the question in Zoom, no. When you save a configuration, you save in the time interval. You don't save the history of zooms. So you can do zoom and unzoom inside Paraver. When you save the window, you don't keep that. This does not characterize the window. This information, unless they have added recently, this information is lost. Okay. And basically, also maybe